So our next presentation for NAB IP Showcase 2022 is from the distinguished Ryan Morris from Arista Networks, and he's going to be giving us an update on best practice for precision time protocol, which of course is crucial to many, if not all, IP video installations. So really looking forward to this. Take it away, Ryan.
Thank you, Wes. Again, my name is Ryan Morris. I'm a systems engineer with Arista Networks focusing on media and entertainment deployments. There have been many lessons learned over the various SMPTE 2110 deployments throughout North America and globally, specifically regarding PTP, SMPTE 2059, 2059-2. And it's really important to understand all of these lessons learned because PTP, as Wes mentioned before, what is possibly the most crucial aspect of any SMPTE 2110 deployment. Many questions are constantly being asked. I'm being asked many questions by my customers about what to do if I have this scenario, how do I make my system the most scalable and most robust for providing PTP timing in events of failures, all of those, every imaginable question. And I'd like today to review some of those best practices and ideas for design considerations. This is a question I get asked pretty frequently. Can I use any switch for distributing PTP? Are all switches created equal? And the short answer to that is no. Not all switches are created equal, specifically for PTP distribution. PTP support, as we know, again, incredibly crucial. Understanding the differences between boundary clock and transparent clock, again, also incredibly crucial. Always ask about scale. When I talk about scale, I'm not just referring only to, can I use all the front panel ports of a PTP switch? That's not all I'm referring to. I'm also referring to, can I support breakouts on all of the switches? So that if I split out all of the 100 gig ports, for example, into 4x10s, 4x25s, can I support PTP across all of them and provide timing to all of those endpoint devices? Very, very important to ask. Understanding if there is boundary clock support or transparent clock support, that's also really important. Transparent clock and boundary clock both really aid in providing, again, a scalable and accurate distribution network for timing. Transparent clock eliminates the switch delay by calculating the residence time for all the event messages going through the switch and updating the timestamp in hardware. This is beneficial generally in two cases. Potentially the top layer of a PTP distribution network where the GM is connected directly into it, or if you're operating tremendous scale in an enormous chassis where boundary clock might not be able to support those numbers. But the issue there also is that a transparent clock does not remove load from the actual grandmaster itself. So you have to be very careful about when to use the transparent clock. Now, offsetting the load from the grandmaster is very important. That's where boundary clock comes in. I generally recommend boundary clock in generally all of my switches, even usually the top tier, because it does provide extra visibility into your network. You can see what the offset from a master is. You can see what the skew is. You can see a lot of really important data in a boundary clock very easily. Also, the switch configuration in a boundary clock is very, very simple. There are differences between transparent clock and boundary clock in terms of how the PTP packets get delivered. In transparent clock, the packets are actual multicast. So PTP is itself multicast, 224.0.1.129. But in a transparent clock layer, those packets are actually in the data plane. So you have to rely on routing multicast packets, which isn't generally a problem in SMPTE 2110 environments, but it just can add a bit of complexity, specifically in redundant designs. Whereas boundary clocks it's all control plane traffic. So you don't even need to have like a unicast routing protocol or multicast routing protocol to go between switches, to go between hops, to go from spine to leaf, because it's all, again, just all control plane traffic. It's more plug and play. And I really like that from a configuration perspective. It really, really helps. And you can configure different interfaces to have different profiles too. It gives you that flexibility. I can say I want this one to be on this interface to be in an AES67 profile, something else to be in the SMPTE 2059 profile, and another one to be anything I want, really. It gives you that added flexibility. And of course, there's also the added security with PTP Role Master. PTP Role Master is something that I always recommend to be configured on any switch port that's facing any end host that is not a grandmaster. The reason for that is I don't want a microphone or a multi-viewer or some other random gateway accidentally announcing itself as the grandmaster. That could be catastrophic for your facility because it obviously won't be GPS locked. Taking advantage again of PTP Role Master is, again, something I recommend in every single one of my deployments that are using a boundary clock. And this also reduces boundary clocks also reduce the chatter. So, again, as I mentioned, 224.0.1.29, it's the multicast used for every single PTP message. I don't want those going all over between every single device. It's not needed. It's unnecessary traffic. Boundary clocks capture those PTP packets that are sourced from the endpoint device and suppress them and just capture them to the CPU. It's really advantageous. It adds a significant amount of scale to any SMPTE 2110 deployment. Question 2. This is something I get all the time also. What versions of PTP do I need to support in my network? Well, typically, there will be PTP version 2. There will be, obviously, we're talking about SMPTE 2110 networks. There will be PTP version 2. However, there's a lot of Dante networks out there. There's a lot of other audio formats out there that necessitate the distribution of PTP version 1, which is not necessarily compatible with traditional boundary clocks. It's important to understand this going into your design because the topology, the design, is impacted by that. Now here's an example. I have my regular boundary clock interfaces going from my spine to my leafs, for example. But that wouldn't be enough if I wanted it on all platforms at least. And this kind of goes back to my previous question of, are all platforms created equal? Especially when we're talking about PTP version 1. Now, in some cases, I need to actually add extra links between the switches just for PTP version 1. Because I cannot, on all switches of all versions of software, have PTP version 1 traffic traversing the same link as PTP version 2 traffic in a boundary clock mode. So therefore, again, I need to have extra links. It just adds complexity to the network from a configuration perspective. It technically can be, a bit of a waste of ports too. And that's why I'm seeing customers now really focusing on deploying newer switches or newer versions of firmware that support something called PTP version 1 forwarding, where I can actually forward PTP version 1 on traditional boundary clock links. And that's really, really crucial because, again, it just saves the complexity of having a kind of like a weird looking design where I have PTP version 2 and I have PTP version 1 traversing over different links. Again, like this drawing where the red would be dedicated only for PTP version 1. The question I get asked is, what does a solid configuration look like? We need to maintain a lot of consistency within PTP. Consistency from the switches to the endpoints, switch to switch, switch to grandmaster. There are different levels, different tiers of PTP that all need to be in sync with one another to create a very robust and scalable network. And again, taking advantage of PTP Role Master. And I want to review some of those configuration best practices here. We have a top tier with a transparent clock and a boundary, or it could be a boundary clock. That can be up for debate. Transparent clock might be a bit faster in terms of the election process. But again, I like to use boundary clocks for some of the simplicity and the monitoring purposes. But as we go tier by tier, always make sure your domain IDs match throughout the entire network. Make sure your GM ID is the same as the spine switch, as the distribution switch, the spine switch, the leaf switch, and the endpoint devices. I get calls where I have devices that can't lock to PTP. It's because a domain ID is mistaken somewhere. Ensure that you have the right intervals set up across, between the GMs and the switches, and again from the switches to the endpoints. Making sure that specifically the announce intervals match. Those are what are really important, the most crucial part for actually determining who the grandmaster is in the network. If you have different intervals, you might see some devices flap between locked and unlocked, or rather locked to my GM ID and going into holdover mode. There's a lot of these different configurations that really do matter. And again, keeping them consistent, making sure you enable PTP on all the interfaces you need, the right domain, all that good stuff is incredibly crucial for any of these 2110 deployments. So what if I have a red and a blue system, red and a blue network? How do I actually connect them together? And how many GMs do I really need in this network? Red and blue networks should be connected together specifically for PTP. Now, I don't want red and blue networks being connected for anything else other than PTP. Occasionally management, but definitely never multicast. None of the SMPTE 2110-20 videos, you can really easily overload some links that way. Now, multiple GMs are definitely recommended. I don't want a facility being, running off of a clock and holdover mode in perpetuity. I do not want that. So I want multiple GMs, but I want to construct my network in a way such that all devices, even if some are operating on red network, some are operating on blue network because of maybe some link failures, they are all always locked to the exact same grandmaster. And here's how we can do it. Just create somewhere in your network, wherever the GMs are connected to. Here they're connected to some spine switches. It doesn't matter. But wherever the PTP distribution is connected to, the PTP GMs are connected to, connect the red and blue networks together. If it's on the distribution switches, connect the distribution switches together. You can also crisscross from distribution switch to, say, spine 1 and another distribution switch to a different spine 2 to get a meshed kind of system. Again, ensuring that no matter how your network fails from a network connectivity standpoint, you are always going to be locked to the exact same GM. And there are some really easy ways of allowing this really to work, to pass PTP between a red and a blue network. You can really just even do something as simple as like option 2, as I have here. Put these interfaces here, these two green interfaces, into a layer 3 mode with no switch port, and don't even put an IP address on there. Don't even allow it to participate in any sort of routing. Just enable PTP, enable the proper messaging intervals, and that's it. And whatever you do between those red and blue connections, the PTP connections between red and blue, never ever ever put PTP role master on there, because you don't know at any given point, because of GPS failures or accuracy, if the clock is going to be going from blue to red or from red to blue. Putting PTP role master, although it's a great configuration for connecting for interfaces connecting to endpoints, it can be dangerous when you're going from switch to switch if the direction of PTP flow changes for any reason. So again, generally a rule of thumb, only put role master on the interfaces facing the endpoints and never put it on the interfaces connecting the red and the blue networks together. What if I have devices supporting LACP? Servers, for example, that are dual home. Can I still use a boundary clock there? That's a new one, and I'm seeing that pop up more and more today. Comes back again to choosing your platforms and choosing the right versions of code for those firmware. At Arista, we have somewhat recently introduced this support for this, and it works beautifully in MLAG designs with supporting MLAGs and a boundary clock, going down to an endpoint that's dual connected. So this is something, again, you need to take into account, understanding what kind of support I need on my endpoints. Are my endpoints all going to be SMPTE 2022-7, or will they be LACP connections? Because that influences your design, and it influences your configuration. Do I really need PTP monitoring tools? Monitoring the network, monitoring PTP, I find I wish I saw more throughout the industry, throughout the deployments. Sometimes monitoring is forgotten, it's overlooked. For PTP, for this, I can't think of anything more crucial than being able to accurately monitor your PTP network. You definitely need it. You need to invest in various tools to monitor your PTP. Now, some of them might be coming from a networking vendor, such as Arista. Some might be coming from the GM providers, or other broadcasting vendors as well. But you need to invest in this. You need to invest in monitoring. Now, from a networking perspective, you can see some really cool things with some of our, like, Arista Cloud Vision as an example, which is able to provide you really cool metrics on PTP. What, for example, what is the PTP offset in real time? So constantly updating, again, in real time. What is the Grandmaster ID? What happened, and what else is important? Not just providing the real-time telemetry, but also a historical record. Not everyone is always going to be on site 24 hours a day. There might be issues happening at 3 in the morning when there's limited staff. I want to be able to, if I hear of an outage, look in my NMS, go back to that time of, say, 3 in the morning, and look at exactly what happened in the network at that time related to PTP. Now, there are also other really cool things you can do, like if your dashboard only shows, if you have hundreds of switches in your network, you don't want to go scrolling through every single switch and look at the Grandmaster ID and compare them all. That might be very tedious, and it's not a good use of resources, obviously, to have someone constantly monitoring that GM ID or other statistics like that. That's where you can come up with really cool scripting, again, like within Cloud Vision Portal from Arista, where we can come up with that customized dashboards almost, where if one of the GMs of a switch doesn't happen to match what it's supposed to be, just put a big, just alert whoever's looking at Cloud Vision Portal. Have someone have a big red marking that says error. That'll get somebody's attention real quick. That some GM ID is really not matched. It's that some GM ID is different from the rest. And of course, obviously, there is also on-switch telemetry. Understanding the tools on the switch, so you can just connect in, look at the PTP offsets, look at the skews, understanding what is acceptable, what is an acceptable variance, and what is non-acceptable variance. All that is important, and it's vital to know about these tools and get them ready and set up during the commissioning process, so you can understand it, how to troubleshoot it before something truly unfortunate happens. So, having an NMS, understanding your on-switch CLI tools as well, and potentially also something that relates more to your broadcast vendor to see how the endpoints are reacting to these sorts of PTP issues as well. So in conclusion, configuring and maintaining a proper PTP distribution network, it's not a daunting task. It really isn't. Some people, it gets a bad name sometimes. But as you follow the correct best practices, you can set it up and it'll be up incredibly quickly and in a resilient fashion. We've done some 3-part webinar series in the past with some of Arista partners, and I highly recommend anyone who wants to learn more about some of the best practices of PTP, what PTP is, and how to commission a PTP distribution network. Look at these YouTube links. They're fantastic. It's fantastic content also. And of course, there's a PTP white paper provided by us that also reviews some best practices too. And finally, consult your vendors. Don't be afraid to ask network vendors, your broadcast vendors, questions about anything related to PTP. We understand it's the most crucial aspect of a SMPTE 2110 deployment, and we're here to help you out and make sure everyone has a great understanding of the configuration process and the troubleshooting process. Thanks everyone for listening today. Appreciate it.
Does anybody have any questions for Ryan?
Is the main difference in IPMX and 2110, is PTP involved in IPMX?
Yeah, so I sit on the IPMX committee. The idea behind IPMX is to relax some of the PTP requirements so that you don't have to have PTP at all of your endpoints in order for the system to work properly. It's generally a good idea to have PTP where your sources are, but it's not necessary in IPMX to have PTP available for all of your destination devices. So that cuts the problem in half, especially when you're talking about distributing AV signals over a big, campus network or something like that. A non-broadcast, yes, exactly. Yep. Yeah, for when you want to be time code accurate, you want to be 2110 and you want to do PTP everywhere. So I did have one question myself. the PTP role master that you referred to, is that a feature that's in all the switches that are out there, or just in some of them?
I can't speak for every switch platform, every switch vendor out there, but any Arista switches that support boundary clock support PTP role master. Whether it's a chassis switch with a 400 gig switch, all the way down to a small PoE switch, does not matter. It's the same version of code, same configuration.
Ryan, thank you very much. Thank you for finishing up our sessions today and for the show. Really appreciate you being a trooper and doing this. So thank you very much.